Today, I'm going to talk about, interpretable machine learning as well as transparency in machine learning for healthcare. And specifically, I'm going to introduce what is interpretable machine learning, and I'm going to introduce one algorithm in a very detailed level so that you can get a sense of how we're going to develop algorithms to understand the algorithms. In addition to that, I'm going to introduce two of our ongoing projects related to how we are going to make use of interpretable machine learning to understand the problems in biomedical informatics. Okay, again, I'm Ben Hu. I'm currently an associate professor in the Department of Computer Science, and I'm also directing the Center for Transforming Data to Knowledge, also known as D2K Lab, in which we are overseeing the minor of data science at Rice, and we are supporting the Master of Data Sciences, as well as supporting a series of student events related to data science. Firstly, why interpretable machine learning? Thinking about the situation, how when a patient walks into a hospital and the medical doctor tells the patient, hey, unfortunately, you are going to develop diabetes in 60 days or something like this, and we don't know why. Our AI systems told us so. Okay, the patient will not be happy because, I need some explanations, right? I need to understand what's going on with my health condition. And I strongly believe the physician will not give a kind of a prediction like this because of lacking of interpretation. And insurance companies will not pay for the bill, and the decision makers in hospital will not be happy about this kind of black box predictions. So that's why interpretation in machine learning systems, in AI systems, are so important to build up like a trust between AI systems and end users. Here, remember, end users here would include different stakeholders. They may include like patients, physicians, insurance companies, and the decision makers in the hospital in biomedical applications. And in addition to that, we also see interpretable machine learning has played a very important role in many, many other applications, such as autonomous driving and many other important applications. And that's why, because of the importance of interpretable machine learning, governments have developed a policy and the regulations, such as the GDPR, released a couple of years ago, as well as the society. We are considering interpretable machine learning a more and more important tool to tackle AI safety problems. Many people here are more or less familiar with how machine learning works in healthcare. And here I would like to give you a high-level introduction of what is interpretable machine learning, how we can make machine learning systems more transparent and have a better understanding of how a decision is made through AI systems. And here we can see in this picture we have two workflows. In the upper side, this is a very typical machine learning process. We have the training data, and based on the training data, our algorithms are able to learn a machine learning model. Here could be like a traditional, for example, SVM classifier or linear regression, any like machine learning models. And by training the model, machine learning model, based on the training data, we are able to make a prediction giving an input, future testing data. Okay, we are able to give in this input, we are able to predict whether this picture is related to like a wolf or just a husky. Okay, this is a typical machine learning training and testing process. And the prediction, this is a husky, will be outputted by the machine learning system to our end users. Okay, in the lower part, this is a typical process of interpretable machine learning, which is very different from the input and the output wise, very different from a machine learning algorithm. And as we can see, what we want to do here is we not only output the prediction of this picture, but at the same time, what we want to do is through interpretable machine learning process, we are able to understand the reasons why this picture is predicted as a husky. It is because of the two regions in this picture, the eye part and the ear part. Because of the characteristics we observe from this picture, we are able to make the prediction. And the interpretation will be in addition to the prediction outputted to our end users. And this is a typical interpretable machine learning process. To formally define interpretable machine learning, here we give out a definition quoted from another paper. Remember, interpretable machine learning is still a very early concept, and it is fast growing. We don't have a formal definition yet. And here, this is the best definition I often use in my talk. Interpretability of DNNs enable us, DNN here refers to deep neural networks, enable us to explain the behavior of a black box DNN model in understandable terms to humans. Why I say this is still not perfect? Because there are several very vague concepts in this definition. And we're scientists, we want an objective definition, right? We do not want a subjective and vague concept. For example, what do we explain the behavior? What is the behavior of a model? Okay, still we need to have a better definition of this. And understandable terms. Understandable, this is a very subjective concept. Understandable terms will be very different from patients to physician to insurance companies, right? Because of the stakeholders, the understandable terms will be very different. That's why we still need to work with our HCI experts, human-computer interaction experts, to understand the information needs, the interpretability needs of our stakeholders to define these understandable terms. And in this talk, I'm going to focus on explain the behavior, and I'm going to showcase how we're going to really define the behavior and how we can really extract the behavior out of application. And here we show a very quick example of how to develop interpretable machine learning algorithms to explain the black box, giving an input, and such that we are able to provide some output in terms of explanations to our end users. And on the right-hand side, we show a very widely used algorithm, which can provide some high-level explanation. And from this picture, we can see two regions representing two classes of data, the blue region and the orange region. And they could be any two-class classification problem. And the curve between the curve separating the blue and the orange regions represents the model we want to develop. And as we can see, this is a very nonlinear and a very complicated curve to separate the two regions, right? And it means our model will be very complicated. This is often seen in deep learning models. And when we have testing cases, they fall into either the blue or orange regions, represented by the cross or the blue dots, representing our predictions for the testing cases. And a very simple way, so the ideal explanation to this classification model will be the complicated and the nonlinear curve. However, it is very difficult to achieve so. That's why an alternative, a simpler version is hey, how about we just understand the model based on their prediction instead of their faithful model, instead of their original model. We just develop a separate linear boundary represented as a dotted line in this figure to somehow provide an alternative explanation to the original very complicated model. So this is called approximating the local behavior around the input instances. So rather than understanding the original complicated deep learning model, we want to develop a simple but intuitive linear model such that we are able to have a basic and high-level understanding of this model. And while we can see local behavior, so here represents a local behavior, okay? They could be very well approximated and explained. Unfortunately, globally, it is not very faithful to the original DNN, right? So how we're gonna tackle this challenge? Later, I'm going to showcase a very specific algorithm, what we should do. And in addition to this algorithm, I'm going to introduce, also through this talk, I'm going to introduce two additional applications related to healthcare. The first one is how we can develop interpretable machine learning algorithms to tackle shortcut learning, to mitigate the problems of shortcut learning. Here we show an example of pneumonia recognition based on the image data, medical imaging data. Okay, the first one is a raw image data. Based on this image, our goal is to recognize whether we have pneumonia or not. The second, so based on some training data, we are able to build up a machine learning model, and based on our interpretation, we are able to see the reason, the working mechanism of the developed AI model to recognize whether the patient has pneumonia or not. It is to really look into the shoulder part. You may wonder why in pneumonia recognition, why we need to focus on the shoulder part, and what is the problem with this model, right? It makes no sense from a clinical perspective. Then this is called a very typical example of shortcut information. I'm going to explain later. The AI model is fooled by the training data, unfortunately, because of the establishment of the training data is incorrect. That's why we learn some shortcut information instead of learning some true information from this medical imaging data. And later we want to improve because of these observations, because of the observation that the AI model learned some wrong information. What we want to do is we want to improve the model. We want to help the AI model learn better and learn correct information such that we are able to provide some trustworthy prediction. So I'm going to introduce later why is it called a shortcut and why is it wrong and how this whole discovery process will be done in a specific application. And the second application related to interpretable machine learning is the fairness in healthcare. Okay, as we know, the importance of equitable access to healthcare has been crucial in many healthcare applications. And in one of our recent projects related to liver transplant, we observe a lot of unfairness, okay, a lot of bias, mainly originated because of the data collection. And unfortunately, we observe a male has better access to female in liver transplant in our existing data. And how we're gonna discover whether or not we have this kind of fairness issues in our biomedical applications, and how we can develop better models to mitigate these problems. And this will be the second application I'm going to cover today. The first one is how can we provide a faithful explanation for predictions made by convolutional neural network, which is a very widely used and a very powerful deep learning model. This picture will show the input and output of our developed interpretable machine learning model. And as we can see, we have the input as a medical imaging. Okay, this input will go through the multiple layers of nonlinear transformation. And specifically, this is a convolutional neural network, a CNN model. And the CNN model is able to predict whether or not this patient has pneumonia or others, probably other disease or just normal. And this is our input. And remember, the DNA model has been established based on our training data. And our whole point here is not to establish the machine learning model. It is to understand how the machine learning model works. That's why our input includes the image data as well as a trained deep neural network. We already trained this deep neural network. We don't want to touch it anymore. We just want to understand how this works. And the output will be the interpretation to find the evidence for prediction pneumonia. So ideally, we want to say, okay, the reason why this input, why this image is recognized as pneumonia, it is because of the specific regions in this medical imaging, such that we are able to help the physician, help the patients better understand what's going on for this prediction. And some traditional algorithms have been developed. So a naive way of identifying the interpretation in this prediction would be, okay, how about we knock out some regions in this specific image? We knock out, for example, we knock out a region here, then we knock out a region here, we knock out another component of this image to see how much influence the knockout process will be to our final prediction. For example, if we knock out a specific region from this image, and the prediction completely changed, It means the knocked out part is very important, is extremely important to our final, to our model, right? So it means like the more influence the knockout behavior is, the higher impact or the more importance of that specific region to the prediction. And through this, like we also call it a perturbation of the data. Through this perturbation, we are able to like understand the prediction very well. However, this process has multiple problems. The first one is like when we perturb the input and then observe the output, we have to go through multiple forward and backward iterations. Because first, we don't know, I mean, we don't know how large the region we need to knock out. That's first. Second, we need to decide how many regions we need to really knock out from this image. This will be like a large number of small regions we need to knock out, and we need to decide whether we need to use like a sliding window or not. So that's why it's a very computationally expensive process. And the second problem we observe from this process is like it will be less robust and computationally very expensive. Less robust here means like I'm not sure whether you are familiar with adversarial learning, in which even though we just knock out like small pixels, multiple small pixels from this image, the prediction may completely change. It means this kind of knocking out mechanism, although it works like in general very well, but in some certain cases, because of the observation from adversarial learning, it may or may not work. That's why it's less robust. Because of these problems, we were motivated to study this problem from the information flowing process perspective, which is a well-established theory in information theory area. How does it work? We consider, because all of no matter it's an image, a text, or EHR record, we just consume this as a piece of information, right? The information, like in terms of the data structure, it's just a vector. Okay, this information will flow through this multiple layers of nonlinear transformation in the deep neural network. This is how the image will be consumed by the model specifically towards the final prediction. And then some key observations from the information flowing process would include the important information. What is the important information in this case? So those will be the information specifically related to the lung part of the patient, right? So important information is preserved for classification, and the unimportant information will be discarded through this nonlinear transformation process. And this is how deep learning really works. That's why how we're gonna really leverage the observations from the information flowing process. And we further have identified another technique called feature inversion, which is to obtain how much information is preserved at each inner layer. And how does it work is like, we can see an illustrative example from this slide. We have two pictures. The first picture is a raw picture. It's clear and it's raw. Okay, we don't do anything. This is just a raw medical imaging data. And the second picture, we purposely make other parts very blur and only the important part clear. Okay, only this part in the left lung part, it is like clear. The other part are like purposely made blur. And what we can observe based on the feature inversion technique is like in the original space. This is the original image space. I mean, no matter it's like the data representation or from human perspective, right? The two images, they are very different, represented by the two distinct like blue dots. They are apart from each other, right? So, however, going through multiple layers of nonlinear transformation, because of the observation we mentioned in the last slide, important information will be preserved towards the classification, right? That's why in the representation space, after multiple layers of transformation, they will arrive at the same point. It means important information, I mean, they are just the information related to our prediction. They will be preserved, and they will be used and utilized by the deep neural network towards the final classification. That's why they are like, they will be very similar to each other, if not identical. And based on the developed like feature inversion observations, here is a proposed model specifically. So we have two identical deep neural network. Essentially, they are the same in terms of the architecture and the weights. However, their input will be very different from each other. The input to the left tower will be the original raw image, and the input to the right tower will be the blurred image, which is come up with a combination of the original image and the mask, and it will be inputted into the right tower. And the idea is like, because of the feature inversion, the idea is like after certain layers of nonlinear transformation, we want to make the output as close as possible. We want to develop an optimization function to minimize the distance between the inverted and the original inputs. And specifically, here comes the formulation, how we can formulate this problem. I'm going to introduce this formulation, and trust me, this is the only formulation you need to worry about through the talk. Okay, so we need to develop the loss function, and the input will be the original image, and the output will be the learned mask, and it can be initialized as a random mask. Okay, the mask means this kind of like a weight matrix in which red color represents the most important part and the blue represents non-important. And this is the goal of our learning objective. And what we want to do is like this function, F represents our deep neural network model, and L0 represents the output of the deep neural network after the L0 layer. And the input of this deep neural network will be an inverted image. Inverted image can be represented, it is calculated based on the original image XA multiplied by the weight matrix. This is called the input, the inverted image, and plus some like noise. So here noise, it is like to prevent the trivial solution happening. And the right part here represents also the output of the deep neural network after L0 layers of the original image. The key idea of this formulation is like we want to minimize the distance between the representation of the inverted input and the representation of the original input, such that we are able to identify the optimal weight matrix in terms of the mask, indicating which part of the image would be the most important. And by solving this optimization problem, we are able to identify, we are able to have an optimal or near optimal mask, indicating the interpretation of this image. And we also have one part to prevent the overfitting problem. Okay, by solving this optimization problem, we are able to like output the interpretation. And we also conducted some like qualitative evaluation. And specifically, we show up visualization comparison with other 6 state-of-the-art interpretation methods. And here we also show 2 case studies. The first image is related to ski, and the lower part is related to a flower cardoon. And what we want to do here is like we compare our algorithm with other state-of-the-art like interpretable machine learning algorithms. And you can see clearly from these 2 case studies, our algorithm is able to like output some like very smooth and very consistent and very representative interpretations related to the classification problem. And also the proposed algorithm, it is independent with any specific CNN model. It can be generalized to like many representative CNN models, including VGG, ResNet, and AlexNet, and it shows very good performance. And till now, I introduced a very specific example how we can develop interpretable machine learning algorithms to understand the important components in our prediction results. And again, interpretable machine learning is still in the very early stage, especially when applying to specific applications. It not only needs the efforts from data scientists, but also the efforts from HCI experts and the domain experts to really come up with a specific tailored, customized solution for a specific application. And here it shows the roadmap of how interpretable machine learning will develop. So we are facing different tasks. We're facing like classification, ranking, outlier detection, recommender systems, many applications. And we are also having like different types of models in our AI for healthcare applications. We are using, for example, CNN models, RNN models, and outlier detection models, and many different types of models. And at the same time, we have different types of data. And the interpretation mechanism for different types of data will be very different from each other. We are having like medical imaging data, clinical notes, and EHR data as tabular data, and many different types of, for example, time series data, which will be covered in the later talks today. And the last but not least, we have different stakeholders. As I discussed in the very beginning, even for a very simple and the same application, we need to accommodate the information needs, the interpretation needs by our patient, physician, insurance companies, and hospitals. And their information needs will be very different from each other. That's why how we can work effectively with our end users, this will be a very critical problem as well to develop an effective interpretable machine learning application. Okay, next I'm going to discuss how we can really make use of interpretable machine learning algorithms and techniques for solving shortcut learning mitigation problem. Again, come back to this example. The first one is like, this is a raw image, and the application is we want to do pneumonia recognition. And unfortunately, our AI model was like too smart. Okay, it just takes some like a shortcut path, because the AI model was like too smart to identify a shortcut feature, which is a hospital token associated with the patients. At the time when the patient was admitted to the hospital, they will be associated with a token in their shoulder. And unfortunately, in our data collection, we just simply collect the data of those patients, and at the same time, we just take other patients and some like normal patients who do not have like pneumonia in this data set. That's why at the time of learning this model, there will be a clear pattern. With human beings, we may not necessarily identify this in the beginning, but AI model is so smart. It identifies, okay, we do not need to look into the lung part, okay, to recognize pneumonia. Instead of doing this, how about we just directly look into in the MRI data whether or not this patient has a token, has a hospital token. That's why when we develop a very effective, okay, probably 100% accuracy AI model, it only look into this shoulder part. It works perfectly in our lab data because of the data collection was problematic, right? It works perfectly in our lab data. Unfortunately, if we deploy the AI model in real-world case, it will fail, right? Because at the time when the patient admitted into the hospital, they may not necessarily, I mean, if they do not have pneumonia, they may not necessarily have this hospital token. That's why it will fail. How we're gonna really deal with this kind of problems? And again, shortcut learning occurs whenever a model faces a problem on data not expected to be relevant or present. Another example I often want to introduce is like for the modality prediction at the time when the patient is admitted into ICU. Was like the AI model was too smart as well. So when we are giving the patient data, and the AI model will recognize one very effective feature. One top performing feature was like whether or not, for the modality prediction problem, so whether or not the patient, the physician will order a lab test for the patient during a certain time period, 3 a.m. to 5 a.m. So if this patient will have a lab test during 3 a.m. to 5 a.m., so likely the modality rate will be very high. So, I mean, I think the reason will be intuitive, right? If everything is going on very well, it makes no sense for the physician to order a lab test for the patient during 3 a.m. to 5 a.m. That's why the AI model was so smart to identify this very strong feature, very strong signal from the EHR data for the modality prediction. And this is another typical example of shortcut learning feature. And here show why we have shortcut features. Because, for all of in our training data, because, to build up an effective AI model, we need a very high quality training data, right? Unfortunately, in the process of collecting those training data, so we just have the pneumonia patients. All of them, they show this very strong shortcut feature. And for other patients, because we need to collect those data from other data sets to make it like a two-class classification problem, right? Unfortunately, they do not have these shortcut features associated with training data. That's why the AI model was very smart to simply look into the shoulder to recognize whether or not this patient has pneumonia or not. And this will work very well in the experiments, in our lab experiments. But when we deploy this model to hospital, it will fail, unfortunately. And how to mitigate this shortcut learning? And here we show a very simple example. So what we do is like the very first step. What we want to do is like we want to detect whether our AI model has, suffer from this shortcut learning problem or not. And when we have this AI model through XAI, through explainable AI methods, we want to identify which part the AI model is focusing on. And such kind of interpretation will be outputted and fed back to our physician, to our domain experts, to say, hey, the AI model is looking into the shoulder. Does this make sense? The AI model is looking into whether or not this physician is ordering a lab test during 3 a.m. to 5 a.m. Does this make sense or not? To predict our future patients. And we may receive the feedback, okay, it does not make any sense. What do we want to do here? So if it does not make any sense, it means there are some shortcut features identified. There are some problems. What we want to do is we want to do data augmentation with identified explanation. So specifically, we have two classes of data, one with pneumonia, one with others. And for all of them, we will just, for this part, they are originally associated with some hospital tokens. And here, although originally it shows nothing in the shoulder, but to augment the data, to overcome the problem, we will purposely add some noise, such that we want to add a part in the shoulder for all of the patients. To fool the AI model, please do not look into the shoulder. Okay, focus on the right part by developing this data augmentation mechanism. And with augmented data, for all of the images, whether or not they have pneumonia, everybody will have a hospital token. Then the AI model will not look at the shoulder anymore, hopefully. And so that we are able to have all of the data to train another deep neural network and then go through the process again by outputting some interpretation and let our domain experts to look at our explanation again to see whether or not we have the problem. If we are still suffering from the shortcut learning problem, we have to go to step one, okay, to go through this process till the identified model first. Till the model first has very good performance, second, has proper interpretation to our physician. And here specifically, we develop a mechanism to identify shortcut features, and also we introduce a mechanism called a data augmentation to mitigate this problem, to make our training data more balanced. Another example I want to demonstrate here is it's called a fairness in healthcare. We just introduced this piece of work in EMEA conference 2 days ago. And how we look into this problem specifically is called a liver allocation problem. And here I want to show you an illustrative example of liver allocation process, just in case you are not familiar with how this kind of organ will be received by our receivers. So suppose we have 5 patients here. Each row represents one patient, and each column represents one feature. They could be like lab test results or demographic information. And based on this table, these are the patients on our waiting list to receive the liver. And based on this table, a score called a MELD score will be calculated. And for each of the patients, for example, the patients will be assigned as a MELD score, and here is a MELD score formulation. They're just a simple linear combination of all of the lab test results. And based on the MELD score, in addition to other factors, such as the distance, waiting time, age, the doctor will assign the available liver to the patient ranks highest in the waiting list. This is how the liver allocation is done today. And our data shows there are some like unfairness in the process, unfortunately. As we can see here in the table, we have ORR and GFR. These are like 2 widely used metrics to evaluate whether the process is like, so how the process is done. ORR is short for organ receiving rate. It is calculated based on the number of patients who receive the transplant, divided by the number of patients who are registered on the waiting list. And the GFR, it is short for graft failure rate. I mean, ORR, it is the higher, the better, right? And the GFR, it is graft failure rate, the lower, the better. It is calculated based on the number of patients suffer from graft failure, divided by the number of patients who receive the transplant. And from these 2 tables, we show the ORR score for male and female. Unfortunately, we can see male has a much higher, has a significantly higher like ORR score comparing to female. And the second table, we show the 2 statistical transplant metrics by race. And we can see race 2 have a much higher GFR score comparing to race 4. It means the failure rate is much higher. So what is the problem? And there are some like disparity among different races. And we show like some certain races, they show significant difference. And how we're gonna really tackle these problems to make sure the whole allocation process is relatively fair. And here we develop a 2-step debiasing framework for fairly predicting graft failure in liver transplant. And I'm not going to dig into the details, but the whole point here is like we want to model some constraints in 2 steps. The first step is the data representation, and the second step is the model prediction part to ensure that we can have a fair process among different genders and across different races. And we also compare the proposed method with other like machine learning algorithms, such as like linear regression and other representative GTBT, which is a tree-based model, and which has like showing the best performance in many applications. And we compare our proposed method with other methods in 2 categories in terms of race and gender. And the AUC here AUC is precision, and the higher the better. DPD and EUD, they are like 2 fairness metrics. And from this table in general, sorry, I'm running out of time. That's why I will like conclude very quickly. So in general, we see comparable performance in terms of the accuracy by comparing our methods with other state of art. And at the same time, we see a much better performance in terms of fairness metrics comparing with the other baselines. And that's why our process will like, while we maintain the prediction accuracy, we also improve significantly in terms of the fairness metrics. And future work can be extended to other post-transplant outcomes and other organ transplant, because our study focused on the liver transplant. And this can be also extended to other organ transplant problems. It could like help other medical resource allocation problems. And yeah, in general, today I'm introducing like interpretable machine learning, and in my lab we are also working on automated machine learning problems. At the end, I would like to thank my students, collaborators, as well as funding agencies. But surely everyone attending the talk, any questions will be very welcome.
Thank you very much. Let's give a hand of applause. Thank you for your talk. We can get 1 or 2 questions from the audience, and people can also meet Dr. Hu during the break.
Yes.
Where? Okay.
Thanks for your talk. I was curious about the part about data augmentation for the shoulder tag.
Yes.
Did you add this feature manually, or do you use an algorithm to?
Yeah, if we are able to identify the shortcut feature, we can just simply add them manually. I mean, manually here means like we know this feature, and we just use algorithm to add this feature to all of the patients who are not associated with this feature. So this can somehow fool the AI algorithm. Okay, this is not an important feature anymore. Please please focus on other important parts. Now, this is a simple idea.
We have 1 more question we can take.
So in the feature importance part, do you have a way of measuring how good you're capturing the feature importance? Because you can always, cherry pick good examples and show everyone. But in a way, do you have a strategy or a way to figure out, okay, this feature importance model that I have a way to show why it's better than other models, not just by eye, but like a really, I don't know, some sort of measure?
Yes. Yeah, this is a very good question. It is related to how we are going to evaluate the performance of the interpretable machine learning algorithms. So how we can demonstrate that our algorithm is better than other interpretable machine learning algorithms. And typically, we will have 2 categories of evaluation metrics. One category is associated with subjective measures. So we hire some domain experts to manually look at all of the cases we identify to see whether or not, so which algorithm, the output by which algorithm makes more sense comparing to others. This is subjective. And some other objective evaluation represents we have some label data. We already manually labeled the important part of these images, such that we try to say, for example, out of 5 algorithms, which algorithm will be able to accurately recognize the most important region of these images. And there are many similar metrics developed for different applications. And we have wrote an article a couple of years ago related to how we can evaluate the effectiveness of different interpretable machine learning algorithms. And you can refer to my website for searching that article.
Okay.
Yeah.
Thank you very much. Let's thank Dr. Hu again.